And there are 13 students here. I think that's a good start. All right, so I said I would take your questions today, and then we could go into module 5 on regression, and I can do an overview, and I'm going to show you about Excel, how to use Excel for linear regression to get results, and also do it on your calculator. But things start pretty much over back in module 3, the unit or the material I call GDS, Graphing, Representation, and Descriptive Statistics. So do you have any questions regarding module 3? Any homework, quiz questions? Check the chat. Well, that's good. So what about module 4? Normal distribution.
Hi, Professor. I have a quick question about module 4.
Mm-hmm.
I just wanted to clarify a confusion. When we use the C table for the C score, you know that the table gives you the values to the left, but if you need them to the right, then you would have to look up the opposite sign number. For example, if you got a -1, then you would have to look up for the +1 if you want the values to the right and subtract.
Or so you can look it up on the negative, or you can subtract the value you got on the left from 1. It's one or the other. Don't do both.
Okay, perfect.
Yeah. Is that okay?
Yes, because I was just wondering, so you do it if you want to get the values on the right, if you want to get a greater than value.
Yeah.
Okay.
Yeah. That's a standard. I mean, it sort of depends on the question, but that's pretty the standard approach. So are there any questions about this unit? Oh, is this module 4? I should. Sorry, I'm deciding where I want to start here. Okay, this was.
Professor, I also have a doubt in the box plot. I know the length vary from the data that we have and the 5-number summary, but the width, it depends on what?
The box plot?
Yes. That one.
Here, so it depends, right? So if you're doing an outlier box plot, if you're doing the regular, let's look at the regular box plot first. So this is a regular box plot. The width would go from minimum to maximum. The width of the IQR goes from Q1 to Q3. So it depends what you're talking about, right? The width, if you use the outlier box plot, you go up till here. This limit is 1.5 times IQR. This distance here. So there's different widths.
So you can use 2 formulas to find the outliers on the right or the left side, right? The Q1 plus or the Q3 minus and the 1.5.
The other way around. Yeah, Q3 plus or Q1 minus.
Okay, perfect. Okay.
So Q3 plus 1.5 times IQR or Q1 minus 1.5 times IQR. But either way, this length will be extended either way because that's 1.5.
And that length, yeah, exactly. That was my next question. That's 25% regardless of the length. It's just 25%.
Well, hold on. Let's be clear. The thing that's 25%,
Oh, the first one, I'm sorry.
so this is 25%, this is 25%, this is 25%, and then this till the end is 25%. It's really long because there's a lot of variation, but it's still just 25%. But this is Q3 plus 1.5 times IQR. So it's going to be, well, it's not really clear because we know IQR is 50% of the observations, right? This is 50% because this is 25 and that's 25. But doing the 1.5, I don't know where I'm taking myself. So we don't really know how many are in here. But we know all the way to the end is 25%. Did that answer your question? Did I confuse you more?
Thank you. Yes.
Okay. All right, let's see. Yeah, so I put some, like, you're getting the idea that my assignment questions are not that hard right now. The most challenging thing you're going to do are the quizzes that I put online. The homework are not that challenging. Maybe for Noor they were a little bit. I don't know if you had a chance to do the midterms. You should do all of those after this test or while you're doing this test. The midterm problems are all at the end of regression, so you should get that far this week. I mean, before Wednesday. Well, Wednesday is when I said the test is due and the assignment is due. So you really do need to know regression. Where am I going? I want to go to the platform. I'm gonna have to log in again. It's so annoying that they logged you out. Okay, so what was I doing? I was going to show you the midterms. Okay, and we can answer I can answer midterm questions too. All right, so this is how far you should be. You should have got this far and even tackled the midterm questions. So up until here, are there any questions? Oh, there's a question in the photo. I didn't see. Interesting. So that was just yesterday. Let's see. Oh, that's assistencia questions. I'm going to say to me. Okay, they're just looking for me. Oh, I thought they were actual questions about problems. All right, that's all right. Back to here. Okay. All right, so no comments, questions. Good morning, Maite. So let's do what I planned then, is to take you back. So from the module, module 3, you should have had the introduction to looking at 2 variables at a time. And I had this discussion. Does anybody have any questions about this discussion? I made a video, edited video, or a pre-edited video about explaining this page. Did you understand all of this? Anyone want me to repeat? So we go from here. This is a launch pad for what we do next in module 5. I have a couple of questions here. And then I get us into module 5. And I focus module 5 on actually calculating and understanding the calculation of the relationship between two variables. Now, we only focus on this class on a relationship that is linear between two quantitative variables, okay? And we gather our data and we produce a measure of the strength of the trend or the direction of the relationship and the strength of that relationship. The direction is seen by the sign, and the strength is seen as how close that number is that we call R, or correlation coefficient, how close that number is to the extremes of -1 or 1. If it's close to -1, then it's perfectly, or it's close to being perfectly negatively correlated. And if it's close to 1, then it's perfectly close to being perfectly positive correlated. And this is how we calculate it. And when we look at this, what do we recognize about this calculation? What symbols do we recognize here? So we just left unit 4 where we learned about the normal distribution. And even earlier on, I talked about z-scores. What these actually are, the data is reduced in each variable to its z-score. So it's a relative measure of how far the value is from the expected value. So how unusual or deviant it is from the mean. So these are the z-scores here, the standardized values, is another way to say it. And what do we do with those values? We multiply them, and then how would you refer to what we're doing here? So we're averaging them. This is like an average. So I'm treating X and Y exactly the same. I'm reducing them to a relative measure, a measure relative to their expected value or their mean. And I am doing that by standardizing each of them, and then I'm averaging them. And I'm doing the same thing that I argued for other samples. For samples, when we calculate the standard deviation, sample standard deviation, when I average, I have to reduce this by 1. Otherwise, my estimate is considered biased. That it's in repeated sampling, on average, I'm going to be off, and this helps adjust for that. It corrects for that. So what about R? I go through and talk about what about R? Doesn't matter between which one is explanatory and which one is the response when I calculate R. I'm treating X and Y identically. They get the same treatment in this calculation. However, when I try to estimate, or I estimate the linear relationship between them, or the line as a prediction line between them, to use in making predictions of values of observations that I don't have for the response variable, then it does matter. It does matter which one is X and which one is Y. And the way to know which is which is I should be asking you, plot height versus cups of milk, or plot income versus age, right? So the first thing that I say, or I say against is another way. In Spanish, I don't know if you say por, maybe, but you're going to say y against x. So that's the order. It does matter because what we're trying to imply, although correlation does not imply causation, what we are trying to do a lot or often is suggest that this X is motivating Y. Okay, so I'm not trying to say that that's necessarily the case unless I have an experiment. I can't prove that, but there's a lot of theory in economics and in other disciplines that defend, after years and several data sets of being collected, we establish that there is a relationship, and it does appear that there's something going on. And then using those models, we explore those relationships, and we do it in a causal way. Although I cannot, just taking two variables and throwing them on a graph, say one causes the other. I hope you understand what I mean. Because economics pretty much depends on economics and then all of the disciplines that come from there, like finance, that we depend on those relationships and studying how they are interdependent. And usually we pick which one is X and which one is Y, and it has a meaning. So in finance, we often say, the market influences the returns for a business or a firm. So returns to the firm in terms of return on investment and returns to its investors. Okay, so we would make X the market, some measure of market performance, and the Y would be those returns that we're monitoring. Okay, we're going to talk about that towards the end. And okay, so that's what we're doing. We're not calculating the relationship between variables that are not quantitative, okay? And often students forget that. It happens all the time. As graduate students who are, I guess, trusted, PhD students, doctoral students who think they learn the basic in statistics, but they forget some of those fundamental rules about when to use which statistics. You cannot take something like a nominal variable where people have answered yes or no to a question and relate that to gender using R. It's just, you can't do that. Okay, there are other measures for that. I don't get into them in this course, but you can easily, after this course, look into how would you calculate a good measure of a correlation with variables that are not quantitative. Okay, so the first point is X and Y are treated the same in general. Calculating R doesn't matter which one is X and which one is Y, but if your goal is to develop a prediction line, then it should be clear which one is X and which one is Y. There's a reason for it. Okay, so variables must be quantitative. R has no unit of measure, so you don't say R%, you just say R. And I just show you here, even in the numerically, we're canceling units because we're dividing or standardizing. We're converting each of these to a standard deviation from the mean in its direction or its variable. So direction is all about whether it's positive or negative. When two variables are positively associated, in other words, when one is above average values of when one is above its average values and the other is above its average values at the same time, those trend together. And I believe I described that using this here, these charts. So this is how I analyze this. So let's say I didn't have the calculation of R. Just looking here, I'm going to divide and identify the mean in this direction. So I get all the different values of X and calculate the average. And then in this direction, do the same thing. And let me do that again. So let's say that's the average in that direction. And then I ask the question, what is the tendency when I'm going to mark this as X bar and this is Y bar, and I say, let's see, when X is above its mean, so when the values for X are higher than average, where does Y tend to be? High or low? And we see, well, it's kind of scattered. And that is a description of R not being perfect. Okay, it's kind of scattered, but it's mostly low. So when X is high, Y is low. Low values below its mean, in other words. So we use these as reference. But it's not perfectly low, but it's there's more observations below than there are below above. And when X is low, Y is high, you see. So that inverse relationship, it comes out as a negative R. Okay, so now that's the graphically looking at it. Now let's look numerically how that works. And that's what I discuss here. First, just to say, strength is measured by how close it is to -1 or +1. If it's 1, it's perfectly positively linear. If it's -1, it's perfectly negatively linear. And otherwise, there's no relationship. And all this is established after making a graph. We always graph first to be able to say any of this. If there's not a linear type looking relationship with a trend, you don't use R, or you can just say R. If you did calculate R, R would be 0, or you would be surprised if there is a pattern, even though there's no linear relationship and R will be 0 here. Be careful, you still need the graph, because if you don't have the graph, you'll miss the fact that there is a relationship. And ultimately what we're looking for is relationship, not necessarily lines. Lines is just the easy go-to. We start with lines, but in fact, there is a relationship here that could be used to make predictions. So I have several examples in the notes about making predictions, and we can discuss this in a moment. So this is what you expect. You know, if you see something like this, you can say, there's no linear relationship, there is no relationship at all, R would be 0. When you calculate, you would find that out. In this case that I describe here, if I was to cut the data in half here and cut the data in half here, you notice every quadrant is full. That's going to show that really it's going to end up with an R very close to 0, which you shouldn't be calculating because it's misleading you. That R doesn't mean there's no relationship. It just means there's no linear relationship, but there is clearly some pattern here. All right, so I'm just jumping between my modules to tie it back together. All right, so notice in calculating our relative measure of a relationship between two quantitative variables, R measures the strength and direction of a linear relationship, not a curved or clustered relationship. Now there's other measures for that, or there's other ways to get estimates of that. And I have in the notes I mentioned that, but I don't go heavy into it because this course requires me to teach you a lot of fundamentals, a lot of the underpinnings of what is done in statistics. And although essentially what you do in practice is regressions, we probably be looking for relationships and regressions. conducting regressions. That's not enough. I mean, you're going to do it all wrong if you don't understand the foundations of what you're doing. Okay, so I spend more time on that than just making regressions. Okay, so notice that the formula for R depends on the mean and the standard deviation. And since we know those are not resistant to outliers, they're influenced, so too will R be influenced. So we got to be careful about outlier values. Once we look at a graph or scatter of the data, scatter plot, we have to determine if we're going to keep observations. We investigate if there's weird observations, and we decide what to do about them. So there's a lot of that discussion. What is an outlier when we do regressions, and the subsequent investigation. You might want to drop outliers because of measurement error. You might want to create, so measurement error is when you actually didn't measure the observation properly. And that we saw measurement error with the NewCom data. Early on, the measures weren't taken properly, and there were 2 errors that eventually we dropped. But there could be a data entry error, which you could easily correct, and you can do that if you have your original documents where you collected the data, and go back and look and correct your errors in the spreadsheet or the database that you're using. And then sometimes you just shouldn't use data because either it doesn't apply, or you want to limit the range of your analysis, so you just leave data out. But you'd have to explain all of that in your report, what you did. So just a brief discussion here about the effect of what we're going to call an outlier, or what we call an outlier, or a deviation from the overall pattern. In regression, we give it a special name, an influential point. And let's see if I can say a little bit about that. So let's say you have data that look pretty much trending up. And I have several examples later, but let's say, so one of them is, I'm going to add so I'm going to add effluent. I'm going to add a chemical to gasoline, and I'm going to see how it reduces emissions. Okay, so pollutants, and this is I think reduced pollutants. And this is chemical additive, something that we put in. Okay, so the trend is clearly positive. You're achieving a reduction. Well, let's say we just double, what our chemical, and we have an observation out here. So, all studies are limited by the funding for the studies, right? Or the personnel that you could assign to doing this study in like a manufacturing plant. So, you just want to see, let's say we just want to see what happens if we had this much. We jump out here and we take another data point, and, what's happening if I add this much and this much. And so what's happening is that the behavior changes, right? The relationship was linear, but then at some point, it possibly drops off, or it just goes flat, or maybe adding even more just makes it more polluted. Okay, so you'd have to get enough data points to see a pattern. But essentially, so what does this accomplish? So what does this do? If I talk about this relationship being linear, and I imagine a prediction line, so I can use this prediction line. Let's say I think I can use that prediction line. So it means when there's no data, and I want to figure out, what if I add this much here, how much can I expect to reduce pollutants? And I predict up here. Well, maybe that's not the case. Maybe the pattern changes earlier on. So you got to be careful not to use this line or this relationship too far away from the data. And then you might want to explore if something strange happens to even try and make this that's my X star, make this estimation. Okay, so this is like a prediction. And the way I calculate the prediction is use the linear equation that I create. And we usually use the symbol y hat for predictions. And we do that for data that we don't know. Observations we just don't know. So we get, let's say we're able to add a little more chemical at this level and want to predict what we would get. We might want to go ahead and do it. Maybe we go ahead and do it and actually add the chemical and get our value. So if we do that, let's say we ended up here. So we would call that has a name, that's called the observed value. Oops. So we, if X is a certain level of the chemical, then I actually get this as an observation. So I can plot that. And already you see it's kind of off of the line, which is interesting. So maybe things start to change here. Maybe the pattern is to go and see my yellow line. Maybe it goes like that. And I don't know for sure, but it's something I can explore by getting money to do more study on it. Or I could try and estimate and then check with just a few values to see if it follows that pattern. It doesn't necessarily have to follow a very even pattern. It can be really scattered about, but again, every data point costs money. So to think about that. So I'm not going to talk about estimating the yellow curve. I'm just saying we're going to focus on the line and the limits of that line. Okay. So the other thing I want to tell you about this graph is that we have the prediction value that's an open circle that I can use this line that we're going to talk about in a second. I'm going to use the line to predict it. This observation is actually observed. Like I actually go ahead and add the chemical at this level and see what happens to the reduction in pollutants. And then the difference between these has a name. Does anybody know what the name is? So we give it a name because it's an important thing. That's how, the error, how far off you are from that prediction. So in English, we say, if a little bit is left over, this is a little bit off, it's known as the residual. And the residual is equal to the observed Y minus the predicted Y. And it's done, well, in one sense, the way I always remember this is in statistics, we often do things we write in alphabetical order, like our symbol. And so it's observed minus predicted, O comes before P. So we use, and I guess in Spanish it's the same, observado. How do you say prediction? Estimado, so it doesn't work. So the other way to remember this is that we want it so that the values below the line have a negative. And that's another way to see it. So these will always be negative. So I'm going to put my symbols in. Well, I guess it's here. So I can use y hat minus y predicted. And these will be, the residual will be positive if the observation is above the line we call the prediction line that we're going to talk about in a second. And it's going to be negative if below. I'll shorten what I was going to say. And that's what's going to happen. If I take y observed, which is this one, and I'm taking the y value, right? So that's here. This is y observed. I gotta move some of this. Any questions? Are you following my discussion right now? And this one is y predicted. To remind you, it's the symbol I use for predictions. And notice if I subtract this one by that one, it's going to be a negative, right? Okay, so any questions? So notice what's going to happen. Notice my green line is just here. And around the data, it didn't include these. What if I try and include these? What will happen to the line? So what is my line? My line, the prediction line, is computed so that it is close. It's because there's many lines I could draw, right? I could draw this line, I could draw it like this way, I could draw it like a little more like this. What's my goal? Mathematically, we are minimizing the error. We minimize the distance between the line and all of these different points around it. So we're minimizing the residual, but in particular, we're minimizing the squared residual because the line fits or floats evenly between all the points, the best line. And now this line is determined with calculus, and I don't expect you to do calculus, but calculus has some really neat results that you can use at a very simple, in very simple terms. Okay, so we're going to talk about that for the linear regression. But that's what the line does. It floats evenly between these points so that the distance between the points above and the line is the same on the top as on the bottom, the distance between the points and the line. And the fact that the residuals above will be positive and the residuals below, the distances will be negative, we can't just add those numbers together and minimize. So it's kind of the same argument I used when I talked about the standard deviation. We have to square, right? Because those differences, if we add up to minimize these differences, so you think about taking the residuals between observations and the position it would be on the line, and this one would be a negative, and we would add it to ones above, those would be positives, and they would actually cancel each other out. So if I wanted to imagine a piece accounting for each distance between, let's put a little bit more data around. That was not successful. So this distance will be positive, this distance will be negative, and if I think about, I want to add up all these distances, but the magnitude of the distance, I don't care if it's a positive or negative residual, I just care about the length. So to get rid of that sign, I have to either remove it, like taking the absolute values of it, or what we do in statistics is we square. So this is the line that minimizes the square residuals. And you use calculus to do that, because calculus optimizes. It's a method of optimization. It's finding minimums and maximums. Okay, so don't worry about that because you don't have to do that. It has very neat results that we will use. So let's say we wanted to include these extra points. So we need to float a different line. Now, how would that line fall? Notice I'm gonna make an estimate of the line. So now the line has to do this to include those points and be close to those ones too. Maybe it's that one, or it's got to do this. So what happened to the line as a result? What happened to the line?
It shifted.
Okay, so it fell, like it dropped, and it shifts,
Yeah.
not shifts parallel, but it drops or shifts like dropping. And so so two things about lines. When we talk about a line, we talk about where it hits the y-intercept. So what happened to where it hits? It changed, right? And the other thing we talk about on a line is the slope. What happened to the slope? Did it go up or down? Did it go up or down?
Down.
Okay, it went down, right? So it's flatter, it's going to the ground. So two things happen when we include, when we look at lines, right? When we look at what happens to lines. So the slope is flatter, and significantly, the y-intercept increased. And one more thing, what else what can we tell somebody about what we observe here? So the slope is flatter, the y-intercept increased. I should write the whole word because maybe you don't know what I'm saying. I'll just say changed, in this case increased.
Yeah, the R value is gonna be lower now because the correlation.
Very good. So the other thing to notice when we're talking about these dots and not the lines, because really it's the observations that we care about. Now it went from a very tight, strong relationship on this line to a very scattered relationship on this line. And that is going to wreck our R. Our R is going to be closer to 0. So these are the kinds of things I want you to understand when you walk away from this course. Making calculations is part of it, yes. And I want you to be good at that too. But once you forget how to do that, I still want you to remember this type of analysis, okay? So R is now closer to 0. So you have to make an executive decision if you're going to use those points to estimate a line, and you probably will not do that, right? It's not a line anymore. Once you have these new observations, the relationship changes. Okay. You can either take a screenshot, you can ask me a question, because what I'm going to do next is just let's calculate R and let's calculate that line. And I'm going to show you, we're going to just go using, we're going to use the calculator to do that, and then I'm going to show you in Excel. But don't forget what the purpose of the line is, right? And its limits. Some people say, well, if you start looking at variables or data, 2 variables at a time, you're going to find that your R's are really low. You don't get, in reality, perfect relationships. If you do find a perfect relationship between data, you should probably check to make sure you didn't make a mistake. But most of the time, data looks like, and some of the data sets that I give you, it's like, is there a relationship there? Is that a relationship? Is that a linear relationship? So data. So is R of, so be a positive 0.4. Is that a good R? That's kind of the question. And a rule of thumb for relationships. So remember, you only calculate R if you see linear first in their scatter plot. And then you have to do kind of an analysis to say, is that a relationship? A linear relationship? So this type of thing is a rule of thumb that some people use to say you have a good relationship, a positive relationship. So R, let's say, so for example, let's say N was 100. What would your R have to be to identify a relationship? What does this equation say? Let's put in the values. So what this means is there is a relationship if R is greater than 0.2 or R is less than negative 0.2. So 0.2, so just for even 100 observations, you can claim there's a linear relationship. If the graph shows you that, you can claim a relationship or a particular linear relationship as long as R is more than 0.2. Now that seems really low, but this is, like I said, R's are really low in practice. So this is what we'll say, there's a relationship worth discussing or reporting. If R is greater than 0.2 or R is less than negative 0.2. All right, so let's, if you guys are good with that, I'm going to go into calculating R. I have a bunch of exercises here where you go step by step. I'm going to just do this one and leave the rest for you. Let me see. This, I have a video about lines. If you need to go right back to high school and remember how to make a line, given a point and a slope, and then this, and then we have some exercises to look at. And I said, you know, you don't have to, this material here, I'm going to stop at slide 9. This other material I'm not going to get into. It's very theoretical, and we have so many other things to do, but I put it here for students who already know regression. They want to tie it to what they've learned before, and talk in particular about economic relationships. So I talk about curve relationships, how to transform data. That's all optional. I'm not going to test you on any of this. And then I'm going to go to page 19. So, and diagnostics. So between 10 and 19, I'm omitting that. So you don't have to study that. Well, I don't say omit because it's optional. I shouldn't say the word omit. Okay, so let's see here. Oh, let me get the data first. So here are data on insects, fossils of insects, and we have measured their leg bone and the arm bone, and arm bones are longer on an insect, than they are on the leg bones, right? So let's take this data with us, and what we're going to try and see is if there is a strong relationship between the measure of leg bone and arm bone in proportion, because that will say that these are likely from the same species of insect. Just have so you just have some bigger ones and some smaller ones, but the proportional length between the arms and the legs is the same. And so we explore that, we make a graph, and you'll see if you plot this, which you should do, putting humerus versus femur. So that means that humerus is the Y, in other words, the arm bone. Yes, Y, sorry. No. Humerus is the, where am I? Yes, that's right. And the leg bone is the femur. Why I always hesitate there. So I put the letters right beside in the chart so I don't forget. And that's why, because Y comes first in Y versus X. And I plot, so I can, so between the lowest one is 38 and the highest is 74. So I've got to go between like 40 and 80 here. So 40, 50, 60, 70, 80. And then on the other, did I just do that wrong? I did, because I was talking about X. So 40, 50, 60, 70, 80. You can have grid graph paper if you like. You can use a ruler. And then the humerus is between 40 and 80 again. So I have the same scale. And roughly speaking, 38 for X is about here, and 41 for Y is about here. So I'm going to put a dot, and it's not going to be perfect, but there you go. And then 56. So halfway between 50. Let me put some numbers here. Just do this as quick as possible, but as informative as possible. So so X is 56, that's about here, and Y is 63, so that'll put me here, right? And then the next pair, 59, which is about here, and 70 is about there. And then 64, which is around here, and 72. You can use like a corner of a piece of paper and put it down and help guide your eye. And 72. So that's just about here. So there's not a lot of data, but it looks like a positive trend. 84, sorry, 74 and 84. 84, and I got to go off here, so I'm kind of off my chart, but I'll put something here. I can clear this up. Clear this up too. See the data. There you go. All right, so it's an upward trend. I can imagine a line fitting to those points. I'd need more data to be sure, but as it stands, it's all I got and it cost me a lot of money. I'm going to write a report. Okay, my scale's really bad, but you just have to visualize that I can make a line there. A nice line, and that these fit very close to the line, very, very close. Now, what's gonna happen? I put the data here, and I'm going to show you the calculation that numerically you're going to see what we saw graphically before. But you're going to see the same thing in the numbers as you saw visually. So I put here all the data. Now this data can come easily out of your calculator, which let's do that. The statistics, I'm sorry, I'm calling it data. So this is the data. And then these statistics we can get out of the calculator. So to enter this into your calculator with two variables, go to second data, clear your second data, clear your data sheet, clear work, and start entering numbers in the pairs. We begin with number 138 for X, enter, scroll down. Now you're going to enter Y. So before, when we used this last week, we used this to do an estimate, a calculation of the weighted mean. Now I'm going to use it to actually calculate the linear relationship as R, and I'm going to calculate the estimates of the y-intercept and the slope for that linear relationship. So y was 41, enter down. I put in the next x, 56, enter down, and the next y, 63, enter down, and 59, enter down, 70, enter down, 64, enter down, and 72, enter down, 74, enter down, and 84, enter down. And then I ask for the second stat. 5 observations, that's my mean that I got here for X. This is the standard deviation from the sample. And we don't use this because it's just a sample of all fossils. So then this is the mean of Y, the standard deviation of the sample for Y, and we ignore that. And then we get some numbers here. This is A, the y-intercept of that linear relationship. So it's a negative 3.65. How do I see that on the graph? And then the B is 1.2 approximately. So let's talk about this first. Okay, any questions about what I did? Does anybody need to see that again? Is everybody okay so far? Okay, so what do you know why I don't, where is A on my chart? So I just made a little sketch, and the sketch that I made first of all, it's not to scale. Second of all, I started at 40. So what I imagined that I did here is I have like I'm really off of the axis. So I really just broke through and started where I wanted to start. Just to note that, like with a, you know, that's not the origin. This looks like it's going to be 30-30. That's not the origin. So what I'd actually have to do, let's put this into Excel so we can see the graph on a nice proper scale, and then we can see that number very evenly. So let's go to Excel. Any questions so far though? You guys good? We're going to put this data into Excel. How many of you know how to do that? And get it and to generate the trend. So I'm going to put, so pull up Excel, try it yourself while I'm with you. If you've not done this before. I'm going to try it. So about centering. Let's put this in 38 for X and 41 for Y. 56 for X, 63 for Y. 59, 70. 64, 72. And 74, 84. Okay, what do we do next? Anybody know? Now this looks a little bit different because this is my iPad Excel, but I should be able to do the same thing. Yeah, because I have insert. And this is on an iPad with OS operating system. This is a Microsoft Excel. Okay, so right, you do insert chart. So you highlight the area. Patricia knows. Does anybody else know? Insert. And I say, oh, this looks different. Insert chart. Oh, over here. I have some options. I want to make a scatter. You see, XY scatter. And you could put labels. You could call X what it is and Y what it is. Femur humerus, right? But for now, I'm just going to do XY scatter. And I'm going to pick, I don't want that. That's not what I want. I don't want to scatter the two. I want to make, oh, something is others. Oh, this is going overkill. I think I just want this one. Yeah, just the dots. I don't want it to chart. I don't want to split the data up. I want X and Y on a scatter plot. There we go. And notice now I have my axis with a 0, 0 origin. Even though the action is all over here, over on the, after 40 and 40, I have plotted the origin. So we can look at where that line hits. All right, so what we're going to do now is we want to put the line on here. So I'm going to highlight the chart and I want to go to elements. Now in your Excel on your computer, it should be in the left corner, and you're going to say elements, chart elements, and you're going to pick trend line. And you see, it'll do it for you in Excel, different kinds of lines. Now notice that's a trend line, and the trend line only is plotted around the data. It doesn't extend like a mathematical line would to infinity in either direction. It just makes the trend around the dots. Why does it do that?
Because if you had more data, the line could look different.
So exactly. So it only plots around the range of observed data. It's reminding you that that relationship only exists around the range of the observed data. Now you could try and make predictions before, it at about 30, you could try and make a prediction where X is like 30, but you should be careful of that. And we refer to that as extrapolation, like going outside of the range is an extrapolation, trying to use a relationship in an area that it's not been observed before, all right? Or in a range it's not been observed before. So that's why it does that. But if we visually imagine extending that line, now I can't do this. I'm trying to think, oh, I know what I can do. I can bring it with us I can bring it out with us. Okay. So if I extended this, it kind of fell, but let's do it. We'll try and do it straight. I'm going to watch. So I'm going to extend it, and like I said, shouldn't do it, but just to show you the intercept. No, I'm not doing a very good job on my. So let's do it from this way too. I need to use a ruler, I think. Let's use a ruler.
Just an idea.
Okay, there we go. Okay, so there you go. So I've extended that line, and you see now all right, so now you see, not perfect, but this should hit. Okay, so this should hit at, what was the value for the intercept? So if you imagine this line goes down, this is A equals negative, whatever it was. What was it? 3, so it's almost negative 3.66, let's say. 0.66. All right, so that's where it's hitting. All right, and then the slope we found on our calculator was 1. 1.2. Okay, so that's from Excel. Let's see if we can get that information from Excel. We can. I'm just going to show you how to do it. Do you have any questions about what I did here? So I wanted to show you, even though, like I said, you shouldn't be extrapolating, I want to show where that value, oh, I shouldn't have done that, where that value of A comes from. So it will cross the intercept here, but we should only make predictions in the blue area. So back to Excel for a minute. So now let's get the least squares regression line. So I'm going to go back to the elements and I'm going to go back to the trend line and, oh, it's not allowing me. I didn't, no, there's a way to do this. Maybe if I just touch it. So this is the problem with me doing this in my iPad. Chart highlighter. So in the regular Excel, you can choose to show the line. Okay, I'm gonna have to do this on my computer as well. Give me a minute. I mean, it should, Excel on the computer or the iPad should have the same features. It's just a matter of finding where they are. It's going to get us to the same place. Okay, I'm going to share my screen. Okay, so on my computer Excel, here I have the same thing, done the same way. And then I go to add chart elements on the left corner here, trend line, linear. Oh, because it says more trend options. Okay, so then I pick more trend options. I don't think I saw that option. And then on the left here, I go to the column type looking graph and ask to display equation on the chart, set the intercept. No, I don't want to do that. And the R square value. Okay, any questions? Yeah, the options are not available on the iPad. So I can move this little box of data away. Can make it bigger, or let's put it up here. All right, so you have the line, 1.2 is the slope, x plus a. A is the y-intercept, negative 3.65, and there's r squared. This is the squared r, literally. And so let's go, you don't have any questions? So if we go in on our calculator, what would be the r? You'd have to take the square root of this to know the r. It's pretty much 1, right? This is like, you could round this to 1. So the square root of 1 is going to still be 1. Any questions? I could not get that in my iPad.
You can also calculate the square root right there in Excel.
Yeah. You mean like this?
Yeah.
Square root?
Yep.
Yeah. So square root of 0.9883. So 0.9. Sorry, I have my caps on. Function I used was all right. So, okay, so a couple of questions here. First, I'm going to go to my phone, to my back to my iPad and show you that I got that R 0.9883. And then I want to talk about what R square is. So back to our, so we got A was negative 3.66, B was 1.2, 1.1969. I mean, it's pretty much 1.2. And R is 0.9941. And the numbers are slightly different, probably because Excel keeps much more decimal places. I'm not sure, but they should be similar. Rounding, this would be 0.994. Interesting. They should be the same. 0.994. Oh, it is. Sorry, it is the same. Yeah, 0.994. It's 414. And in Excel, if you remember, let me do that. Let me type. I'm going to write here what it was in Excel. So in Excel, it was R square is equal to 0.9883, and this is 0.994. Okay, so there's the R. So it means it's a positive, strong relationship, which we see in the graph as well. Always graph first. So no surprises here. Now, what is R square? What do we use it for? So R square is just the square of R. So you could take this value and square it, pressing the square number. So that's R square. And what is it for? So in this calculations here, I round everything to 2 decimals going through. It's a little bit different, but same. It's still 1 when you round it. So R square I'm going to use the one that's down there. Notes. Is Now, if you do 0.995, you get 0.99. Okay, so this is like a rounding nightmare. So let's take the number. And let's just go with this. So this was R from the data where we made a table. I make a table and I calculate. So I'm going to talk about the table elements in a second. So if I square this, I get 99%. What does it mean? 99% of the variation in humerus, sorry, yes, humerus is explained by femur. So although R is not a percentage, we interpret R squared as a percentage of variation. And this has to do with what exactly you're measuring with R. What you're measuring with R is a standardized covariance measure. So it's looking at variation and it's putting together, and when we square it, it's telling us the percentage of total 100% variation. So it's 99% of the variation. And the Y, the predicted value or predictable one, is explained by the variable X. Okay, so that's the interpretation of R squared. Now these numbers are very close. It's not necessarily going to be the case, and you'll see that in the examples I give. But that's how we use R squared. So R squared is interpreted as a percentage of variation. R we interpret as the direction and strength of the linear relationship between the variables, the quantitative variables. So going back here, just doing everything in a table, let's look at what we get. Now I did all this in Excel. I got all my results already. I got my R, I got an A, and I got a B, and I got the line, did all of that. But what I want to show you is what's picked up by the calculation. So if I take 38 and I minus its mean and I standardize that, what do I get? And do this in Excel as well. So I'm going to get the mean. I can make So I can calculate the average of these values. Values here. And the standard deviation. Now there's many options in Excel for standard deviation. Notice there's a P and an S. P for population, S for sample. You want to use the sample calculation, but by default, this one calculates the sample standard deviation. I think that's correct. Yeah. All right, so mean standard deviation. So what I'm going to do is now you can just do this manually if you're following my directions. Actually, I'm just going to write them because I don't want a problem with references. So it's 38 minus 58.2 brackets. Because Excel doesn't follow order of operations, probably have to set it up somehow. And
If you use the dollar signs, you can use the.
yeah, I don't want to do that right now. I know that, but I don't want to do that right now. So I'm just going to mimic what you're doing manually. 13 point, what I did in the table, like what I did here, I just did 13.19, so I get the same type of answers. 13.19. So that looks wrong. 13.19. So 38 minus 58.20. What happened? 38 minus 58.2.
Right. Yeah, you have switched the.
Yeah, it just because I'm using an iPad, I'm not used to it. Okay, so then here you copy and paste. And it references the column. Okay, let's just do a few of these. And then this one, I'm going to write 41 minus 66 divided by 15.89, which I think I did over here. Yeah. All right, so let's look at just these two things. There's a lot of decimals here. I'm going to get rid of them. So I'll just round everything to 2 decimals. Okay, so what do you see? When X is 1.5 standard deviation below its mean, Y is also 1.5 or 1.6 standard deviations below its mean. So they basically behave in terms of relative measures, they behave the same. Okay. Same with the next pair. It's not just a coincidence because the next pair, when X is close to the mean, so minus 0.17 standard deviations below the mean, or 0.17 standard deviation below the mean, Y is also very close to the mean. It's 0.19 standard deviations below its mean. So it's in the same magnitude and the same direction. And they're doing the same thing. So what happens? Let's copy this all the way down. And so you see these are very similar. Those are the similar. These are similar. These are similar. Those are the most off ones. The rest are similar. So it's not perfect, but they're very similar. So what happens now is we do this multiple, we multiply, do the product of the two z-scores, multiply this one and this one. And what happens is, because they're both negatives, they become a positive. And that happens all the way down. They all become positives. So because they're behaving the same way in terms of direction, when you multiply, it becomes a positive. So that's how you get a positive R, that they're doing the same thing. When X is below, Y is below. When X is above, Y is above. So that's going to work out to make up the product a positive sign. And then when I add these up and I divide by how many there are, minus 1, supposed to divide by 1 less, right? Not by 4, 5, sorry, 4. And that's what I get for R. Now, obviously, we're able to get this sorry. Yeah. You can obviously get this in Excel itself. We did. If you want it like just directly, if you want the correlation, equals correlation. It's not about getting values. What I'm trying to teach you is about where they come from, so you know when to properly use them. Is this going to work? To something. I don't even know. I don't know if that's the command, but basically we got it doing. No, that's not what Corel does. So we'll skip that. How can we get R out of Excel? What is R? So we've shown that it's a measure of the direction and strength of a linear relationship between two quantitative variables. I've shown you what that means. I mean, how we get that, because of the way the formula is set up. You're standardizing the values, and then if they reinforce each other, if the variables are behaving the same way relative to their mean, outcomes are mimicked, then you get a positive R, and then the behavior in terms of high or low numbers turns out that the average should be a positive and close to 1. So what is R then? So that's one way to explain what R is doing. But in fact, I could write this formula a different way that pretty much says the same thing, well, in a different way. So this is R version of the R formula that's good for illustrative purposes. Okay, so I was able to show you that. But in fact, algebraically, I can rewrite this by removing these standard deviations and moving them to the left side. Then what I do is I rearrange, I put this sum of deviations from the mean, or product of deviations from the mean, I put n minus. So all of this manipulation algebraically I can do And then I recognize, well, what is this? So to this point, I've taught you about the mean, I taught you about the standard deviation, but not the covariance. The covariance is what I'm going to talk about right now. So basically, from talking about the correlation and how it is calculated, the correlation is essentially a standardized covariance. The covariance is just the top part, the average of the deviations from the mean. So covariance X, Y now let's remember what the variance is just for a moment. Variance of X is the average of the squared deviations from the mean. The covariance converts, if I can write it like this, rather than having X, the deviations from the mean squared, I'm getting the squared factor by including a different variable. So in the units, it's squared, but I'm using the other variable y instead of X itself. And this gives me, like we talked about, it captures the trend of the relationship relative to the mean on average. And then because covariance from variable to variable gives you numbers that are not easily interpreted, we standardize it. We divide by the standard deviations of both. And this reduces the number to something that's easily interpreted. R is in -1 to 1. And by doing this also, if let's say we were to talk about the units here, if we talk about the measure of the leg or arm bone, this would be millimeters squared in units. When we standardize by SX, SY, again, those are both going to be in millimeters. Each of them will be in millimeters. I shouldn't put it up there. And the units cancel. I hope you're following what I'm saying about the units. So basically we eliminate the units and it's just an index. So this is my stab at, I'm telling you what covariance is, but as it relates to the number we more often use is R, the correlation. Correlation is the standardized covariance. So knowing that, you can get covariance in Excel and then standardize it to get R. But you should be able to get R in Excel directly. I just don't know the code for it. Let me see. Just gonna Google it. Oh no, they're telling me Corel is the way. But I have to do column by column. Okay, so let's try that. So let's do that. Let's get the correlation and let's get covariance, and then we'll just see. You guys having fun yet? So let's do. So let's say I did Corel, which is correlation. What I have to do is highlight this. That didn't work. I have to tell it it's a formula. I have to put the equal sign first. Then I have to highlight this and then highlight this. How does it show it? A comma. Comma. And highlight this and then close. So you got to go column by column. And there it is. So I'm going to write it here for you. Okay. So that will get you the R out of Excel. Why is it different though? It is a little bit different, isn't it? I guess it depends on how it's calculating it, but it's anyway, for all intents and purposes, it's right. Let me make sure it's doing the same thing. So this is the thing, you know, you can use software, but what is it doing? You got to be very careful to know what it's doing. It's not so straightforward. You might think you're getting something. In particular, when you do percentiles and calculations of the 5-number summary, I think I mentioned in Excel, it's like it calculates things slightly different. So follow my directions to get my answers, but are they very wrong? Different? They can be different. So you need to know that. Anyway, whatever. It's pretty much the same number, 0.994. And then
Professor, for the exam, even when our calculation, it gives us a little bit of a different, we can always select the correct one and then you would understand that
look,
it's
if all the exam has been solved manually, so you're not going to get the same exact answers if you use software. So
correct.
that's
but
all I
for
can
the-
tell you.
Right, but for the PDF that we're gonna include, we can include the way we used to calculate it, and even if the number
If you're going to send me an Excel, if you're going to do something in Excel and send it to me, you have to send it to me in Excel. Don't send it to me in PDF because I want to see your formulas.
oh, you mean to copy the actual Excel spreadsheet?
Send me the Excel spreadsheet. Yeah.
Okay, no, because I thought you wanted us to do what you're doing now, just to put the equation next to it. So we don't have to put the equation next to it, we just put the Excel
Just give me
spreadsheet,
the Excel.
and then you
yeah.
can go and step on top of it and see what, okay, that's better, yeah.
Yeah, I don't want you to do a lot of work. This exam should take you like an hour or two. It shouldn't take you that long. You shouldn't spend 5 days doing this assignment. That's not what I'm asking for. Okay. I just want you guys to answer the question, show me your work, and it should all be done manually. If you want to use Excel, that's up to you. But you need to show me, to show your work, then you have to send me the Excel spreadsheet. I don't expect, some students spend a lot of time developing their exam. Don't waste your time. It's not what I need. I don't need you to send me a beautifully crafted assignment or exam paper. Don't make it messy, but you should be able to do it manually completely using the tables for the normal distribution. And anyway, Excel for correlation and regression is not on the test right now anyway. Okay, so what was I doing? Oh, covariance. So if you wanted to do the covariance, so again, you have covariance, just a general, and then you have P and S. P for population, S for sample, but let's do this one. And it's asking for array again, so I'm going to learn from what I did last time and do that one for the first one, and that one for the second one, and see if that works. So that is supposed to be covariance. And so what I'm telling you is that if you take the covariance and you divide by the standard deviations multiplied, you should get the same answer. What I do. As you have to use brackets. Because it doesn't follow order of operations. There's probably a way to set that up, but and they don't get the same number. So what is that? So let's see. This is covariance divided by the two standard deviations. Should work. That's not it. Maybe that's not doing what I think it's doing. So covariance, let's just do the sample covariance. Basically, the takeaway here is that just do things manually from my class. It's a completely different number. So anyway, that's covariance sample. And then you take it and divide it by the two standard deviations multiplied. And there you get the number. So that should be the same. So covariance is equal to I want to copy it. Need to reference the two columns. So I use S for sample to get the right answer. So that was B2 colon B6 comma C2 colon C6.
You don't need the parentheses.
You have some sort of echo.
Yeah, I was gonna.
Just let me finish. Hold on, okay? Don't say anything yet. Just let me finish this. I think oh my gosh, it won't let me do lower cases. It's annoying. I'm just gonna put the numbers in. So because of the rounding, it's going to be slightly different, but I hope you understand what I'm trying to do here. Even if you cover up the numbers in Excel, it still has the, it still stores the oh, it still uses all the decimal places. So the number is going to be a slightly different than your calculator or by manual, whatever you do. But in class, if you ever do a table, just keep two decimal places. I don't expect you to keep more than 2 decimal places. Okay, questions, comments? So all I did was show that if you're to use a table, you can use this formula. You can also do it this way. In this other table, it's the same thing mathematically. In terms of interpretation, I like this formula to illustrate what exactly R is capturing. But in practice, it's easier to just think the standardized covariance, calculate the covariance, and divide by the standard deviations. I have some, and well, in terms of the test, just you can do, you just use your calculator. You can just use your calculator. This would be for the final because this test doesn't have regression. You can use Excel, but don't go overboard. Illustrating, just give me the Excel document that you use to make your calculations so I can see your formulas to see where you possibly went wrong. In this exercise, I just plot this data that shows that the more or the faster you go, the less like you burn excess fuel, or you burn more fuel than if you just drive around 40 miles an hour. This is going to get you the best miles per gallon. Don't drive too slow because you waste fuel. Don't drive too fast. But it looks like driving whatever vehicle it was to get this data, that was a situation. So if you plot this, you get like a curvy kind of thing. And you're going to find if you calculate the R with this data, you can do it on your calculator, you can do it in Excel. The R will end up being 0, but that doesn't discount the fact that there is a relationship here. There's 5 points. Something like that. So from the scatter plot, there's no linear relationship, and R is 0. However, we do see some sort of curve relationship that might be of interest. I make all the calculations here. Here I describe how to make the equation of a line and interpret it. And that gets us over here about the least squares regression line. Okay, any questions about anything so far? Kind of go in circles because I went in circles because I kind of showed you this already. I'm coming back full circle, but what I want to do is go deeper. Every time I touch something a second time, it's to go deeper on the topic. So here's where we started today with data, scatter plot, and this prediction line that is the best fit to the data in that it fits closest to all the points as a result of having it float evenly between the points so that the residuals on the top are matched by the residuals on the bottom. So this distance here, my lines are curvy. Notice that I say that I want your handwritten solutions for the test. So I do want you to do it manually. If you want to support with Excel, you have to send me the original stuff. So these, if I was to put these green dashed lines together, that should equal the green dashed lines here on the bottom. That's how I lie this. That's the line that I pick. So calculus will find this for us by minimizing the squared residuals. The least squares prediction regression line is the best fit as it fits closest to all the points. That is, it fits such that it minimizes the sum of the squared residuals. These are known as the ordinary least squares estimates of A and B. Now, I actually should have hats on everything, but I just didn't want it to look too too messy. But essentially, we just have a sample, and with that sample, we are getting this line with this intercept and this slope, but they're just an estimate of what, if I had more data, a different line, right? If there was more data, this would be slightly different. So I actually should have predictions, hats, chapeau, or sombrero on each of these letters, except for the X, obviously. So there's three conclusions that we take from the calculus of this problem. First, because this line fits closest to all the points in both directions, it's going to cross through the point or the position in each direction that is closest to all the values for X and all the values for Y. Because the mean is the center of gravity, it's the balancing point. It's this in that it's the balancing point. What it's doing is it is positioning itself in the middle of all the points. So to be, in other words, in the language that I'm using now, it's closest to all the points. It's the position that's closest to all the points. So if you're thinking about the values of X, this value, this value, this value, this value, this value, this value, the one that's in the middle, the mean, will be the value that's closest to all the points in either direction. So because of that, the point X bar, Y bar, because that's going to happen in this direction as well, the point X bar, Y bar must fall on the line. Then we have this result. All you need to make the equation of a line is a slope and a point. And if you don't know that, go back to this discussion that I have a video for. Equation of a line can be determined with a slope and a point on the line. It can also be determined with 2 points, but we're not interested in that method right now. So I have a point that falls on the line, and I also have a slope. This is a result of calculus that the slope is calculated as the correlation times the standard deviation, the ratio of the standard deviation, but I have to put Y on the top and X on the bottom. So in this way, actually, if R is positive, B will be positive, the slope. If R is negative, B, the slope, will be negative. How do I know that? How do I know that? The chat.
So the R is based on the behavior, is it going upward or downward? And so is the B, the slope.
But mathematically, how do I know that R and B will have the same sign? But yes, true, right? If you know graphically, if the correlation is positive, the slope will be positive. The correlation is negative, the slope will be negative. But mathematically, R and B will have the same sign because standard deviations will be positive. A standard deviation is what? It's the square root of the variance. A variance, the square root of anything will always be a positive. So R and B have to have the same sign mathematically. And interpretation, if the trend is positive, then you're going to have a positive R. Trend is negative, you have a negative R. So usually, you know, in a class that where I give an in-class test, students have to memorize this, and because I don't derive it, and you don't see what's behind the black box of this formula, it's hard to remember why SY is on the top and SX on the bottom. And I just tell the students to think about risk. Actually, in finance, slope is a measure, a slope relationship between returns in the market to investors in the stock market and returns to investors in a particular firm. The measure of the slope of that relationship identifies the kind of the risk of adding that stock to a portfolio of assets that mimic market returns or performance in the economy. So it's a measure of risk. So I get students to remember this acronym, to remember how to put that down. And it kind of helps, you know, SY over SX. Even if you have the formula sheet in front of you or the formula in front of you, might mess up, but this helps remember Y comes before X. So now you have a slope, you have a point, and you can find the y-intercept by making this substitution. So this, again, this is how you would solve this mathematically. You might have to do this. There's some questions where I require you to show the derivation. So you might have to do this. So here's an example, going back to the fossil data that we looked at. This was the mean of X. This was the mean of Y. R, I'm just going to round to 2 decimals, so it's going to be 1. SY is 15.82, SX was 13.19. So the B was 1.2, which is pretty much the number we found in Excel and on our calculator. but this is because of rounding is a little bit different. And then to find the A, we can use this formula or put it into the equation of the line to isolate and solve A, which is close to -4. It's a little bit different than what we got, but here I'm storing 4 decimals. So my rule in my notes is always complete your answer with 2 more decimals than you started. So here, the standard deviations both have 2 decimals, so I ended up keeping 4. So that's pretty much the rule in my notes. And it's just to help you get the same answers of me and not get frustrated when you have multiple steps. All right, so that is that. This is the equation that we started with, the one in Excel, pretty much. Now let's interpret. Let's interpret this. So you guys can practice making these sorts of calculations with the exercises in the notes, the exercises in the homework, the exercises in the practice. Okay, there's lots of practice. But even if you're going to use Excel or your calculator, you still need to remember how to make these calculations, because I might ask you. So how do we interpret this? How do we interpret A? Let's just go with these numbers here. So A equals -4.11. It's called the y-intercept. What does it mean? So I'm asking you a high school question. This is a high school question, but the fact that, sorry, but the difference between high school and statistics and this level or university level is that this line is not infinite, okay? The line, the least squares regression line only exists around the range of the data. The data starts at 40, close to 40. So when I interpret this mathematically, like in high school, I would say when x is 0, y is -0.411. So interpreting back to the data, what was x? X was back here. Right, X was the femur. So the leg bone, Y was the humerus, the arm bone. And the arm bone is longer than the leg bone. So this says when the leg bone is 0 millimeters, the arm bone is -0.411. Does that make sense? So in general, this is what we do to interpret. We say when the x is 0, the y is a, right? Just for the equation. If I put a 0 in here, the y will be this. So that's the y-intercept, but we should never make that interpretation literally, this is far remote from the observed data and is an extrapolation. That literally shouldn't be interpreted, but mathematically that's what it would be, okay? It's an erroneous or a strange meaning. So how can you measure if you don't have, unless the bone was broken, you know, having a bone of 0, you don't have anything to measure. So it doesn't make any sense. Mathematically, that's where it would fall as the y-intercept. Okay, so what about the slope? How do we interpret the slope? So see it like this and say, for a 1 unit change in, remember, because this is the change in y over the change in x. So for a 1 unit change in the femur, I'm going to say increase. Let's do increase. So that's what we got to fill in. So for a 1 millimeter increase in femur, the humerus is negative. Sorry, I put the wrong number for B. You guys didn't stop me. Okay. Blaming you. With the wrong number for B. Sorry. Let's do this again. I was busy setting it up. B is 1.20. Okay, so for 1 unit increase in X, the Y is B. The humerus is is 1.2 longer. Millimeters longer. Okay, so for 1 unit increase in X, the Y is B I'm going to say increase by B. Let's say that. So for a 1 millimeter increase in the femur, the humerus is 1.2 millimeters longer. I'm missing all my prepositions. Okay. So that's my interpretation. And so I see, so what do I do with the R? So that's my A, that's my B, and what does R tell me? This is my A, this is my B. What does R tell me? How do I write about the R? Since R equals pretty much 1, I'm going to round it to 1, this relationship is perfect. And perfectly positive. It's just perfect that so if I decrease the femur by 1, the humerus decreases by 1.2. So it's perfect, it's reliable, it's a reliable relationship. I can bet on the next fossil that I found, it will have a 1.2 proportion between the leg and the arm bone, if it's from that species. So what I do in these notes is I have several questions that I repeatedly ask, and you should be good at answering all those questions. So some other questions I ask is to use the line to make a prediction. And so you use it like the equation, plugging in the value of X to get the value of Y that was not observed. That's how you use the line to predict. Similarly, you can get a residual by making the subtraction, getting the predicted value and putting it in here and subtracting from the observed value, so you guys can practice that. Then I ask, okay, and ask a question about, do you see any outliers? So how are you going to determine if you have outliers? Well, you should estimate the line and then estimate the line with the new or without the outliers. So estimate the line and then estimate without the outliers. If you see a dramatic change, then you have influential points and you need to decide what you want to do about them, given some investigation. I talked about what R squared is. The name of R squared is the coefficient of determination, and it's used to estimate the proportion of the variation of response variable that is explained by the explanatory variable. That's the definition right there. And that's pretty much it. So you get to practice doing this, using the line, making predictions. You can set aside all these pages and get to here and try these review exercises. You can read through them. I believe I look at them in the videos, and that brings you to here. I have all the formulas here for you. Mean, standard deviation, covariance, and correlation that has many different calculations, and the slope. So here I have finance data on returns. These returns are for a particular company, and these are the returns of the S&P 500, which is an index that tracks the performance in terms of returns to the 500 top performing companies or the most valuable companies. So in terms of market capitalization, so that's the value of its outstanding stock. So then it puts them together in an index, like a weighted average type thing. And this represents the performance of the stock market, which is like a proxy for the health of the economy. So this measure, I'm not going to get into this unless you take my finance class, how I get these numbers. So basically this percentage shows that the economy in this period, if you invested in the stock market in a portfolio that mimics the S&P 500, or you can actually invest in the S&P 500 index, you would have had a 15% return. So for $1 invested, you get $1.15 back. And in the firm, if you invest in this firm, you do better. You get a 30% return. In the second period, if you invest in the stock market, you had 99% return. So for every dollar invested, you got 9 cents extra. And then if you invested in BC, you got 18%, so 18 cents on the dollar. So this is the data. Looking at this data, what can you say about the relationship between X and Y?
Y seems to be doubling X
Yes.
every time, every period.
Okay, so it's double. So what is B and what is R if they're doubling? Is the doubling perfect? If it's always double?
Seems to be, it's always double.
So would you say R is probably 1? So what is B? So if you have a doubt, put it in your calculator and tell me what is B, what is R. So put them in your calculator. And tell me. Right, so B will be 2. So let's put all these numbers in our calculator. So let's go back to worksheet. Let's clear the worksheet and put the numbers in. So you can put them in as decimals. And then then get the stats. You have 5 observations. That's the mean. That's the standard deviation. That's the population standard deviation. This is the mean, the standard deviation, and that's the population. Their A is 0, so it goes right through the origin. The B is 2, and R is 1. So look how good you are. Just looking at the data, you can see that. Now you know what it means. Can you get the covariance out of the calculator? How can you get the covariance out of the calculator? If I wanted that, so let's go through again. So let's get, here's the standard deviation. I'm going to store that in 1. And then I'm going to get the standard deviation of y, and I'm going to store that in 2. So I hit store in the number. So I store it in 2 spots. And then I'm going to take the correlation was 1. Remember, the correlation is the standardized covariance. So I'm just going to multiply it by the 2 standard deviations, and that is my covariance. So I just taught you how to use the calculator to get all the statistics on that page. Very quickly. So just like the correlation is the covariance standardized, then the covariance is the correlation times SY/SX. I put X and Y in a very specific way for a very specific interpretation that for a 1 unit change in market returns, this firm has 2 unit changes, right? Now the relationship is always with the positive returns, and if this relationship held for negative returns as well, which I already explained, you shouldn't try to make predictions outside the range of values, but if you did, what if the S&P returns were negative 5%? What would BCE's returns be?
Minus 2.5.
Or the other way, double, right? You told me double. Negative 10%. And so in this way, we see the sensitivity or the riskiness of BCE returns. It's all nice and good and well when the firm does well, but what if it does, if the returns are, if the economy is doing well, but if the economy is on a downturn, BCE does devastatingly bad. So in this sense, but again, it is an extrapolation, and we could say, oh, that's never, that doesn't happen, and we don't have data about that. So it's not so risky, but usually we call this risky. Okay. Okay. Any questions about all of this? So all that I've said basically boils down to using your calculator and getting the numbers very quickly. You can get all this stuff from your calculator. I do want you to understand where it comes from. I do want you to see the pattern and what we're doing and seeing that
Professor,
statistics.
on that extrapolation, I'm thinking that since BCD always does twice better than the market, even if it's -5, it would be -2.5, which is still twice better than the market, not -10. Right?
Not if you're thinking of it as a slope. Just do the interpretation like we did. So that's a good question. So B is equal to 2 over 1. So what if it's -5 or negative? So if I do -5, I'll just do it in percentages. Then what will the top be? That will make my ratio 2. So you've interpreted saying it's better in the sense that it's better because this is better, but numerically this is 2 times. And so it also has to be 2 times in the other direction. And it's a good question. It's good that you're thinking, you're questioning. Don't just don't take my word for it. It's good you're questioning. But in this case, it is like that. Do you follow me? In ratio, it works. But in terms of your interpretation, talking about better, well, it's not better. It's really double. And the direction will send you double in that direction that you don't like, that you don't consider better. Think about it. Okay, so my headphones are.
Can you hear me?
Yeah, we can hear you.
I need to charge. I usually take a break to charge my headphones. My earpods. You hear me? I don't hear you.
We can hear you. Can you hear us?
I can hear you. Okay. All right, so this kind of data where you have the observations are treated as though they're an even, they all have equal information. They offer equal amount of information. This is historical data. This is after it's occurred data. And so I treat each observation as equally important or significant. And that's why I'm using just the regular mean, the regular standard deviation calculation, because there's no greater value to any of these observations. They're all equally likely. Okay, so that's basically the underlying assumption of doing that. But what if your data appears like this? So this should look familiar to what you've seen before. Just realize my cursor always ends up on the middle of the screen. The data might appear like this. And what is this? This is saying that we've taken historical data, we have some modeling, we make some predictions of market returns, we know some things about the fundamentals of the firm, and we come up with this distribution, really. This is a discrete distribution. What we think is going to happen. Now, in fact, there's infinite array of possible outcomes, but we've narrowed it down to 3 possibilities. Either the economy is going to boom, it's going to be a status quo normal economy, or there's going to be a downturn or a contraction or recession. We are most likely we believe it's going to be normal. In that case, returns will be about 8%. In the less likely case is there's going to be a recession where the returns are 4%, or more likely that there's going to be, almost as likely as a normal state, that there's going to be a boom, an expansion of the economy with a 14% return. If these things happen, this is what we expect for the firm's returns. So this could be much more complicated, but I've made it just 3 possibilities. And with this, you should be able to calculate a weighted mean, a weighted standard deviation, weighted covariance, weighted correlation, and weighted slope. Now I'm using Greek letters. Does anybody know why I've introduced Greek letters? I'm treating it like it's the population. This is population data. These are the only possible outcomes. This is their frequency of occurrence. These are their outcomes. I'm treating it like it's population data. And as such, I have to have these other formulas. These are the more general formulas of calculating. And now, that's why I use these Greek letters, because Greek letters are reserved for population statistics or population parameter calculations. So these are like parameters now. Now, how in the world are we going to get these out of our calculator? Well, the only one I know how to do is the weighted mean. The rest you can use Excel for. So I sort of showed you how to use Excel. I did show you how to use Excel. It's just that you've got to put these formulas in instead. Now, I think I have on the website an Excel document where you could use it, where I make the tables so you can rehearse how that's done. But it's basically the same types of calculations, and you can do this manually too. There's only 3 observations, so it's not that hard. But they're the same formulas. The letter sigma is for S, and the Greek letter rho is for R. This is just R. And here you see B equals R SY over SX. So it's the same pattern. This is just longer and messier looking because we have to put a P in there, and then I have to use this longer expression for the sample mean. I mean, sorry, the population mean. I think I have, you could also call that mu, right? It can also be mu with a little x. So this is what I call ex ante data. It's predictive data. But you should also be able to calculate all these things for that type of data. I have these tables here to do it, and I give you the Excel file to do it step by step. Let me see. Let me turn this. So let me double check that it's visible for you that I have this. Practice. So there's a number of exercises. I believe I have all the solutions up for the exercises. If you find that there's a place where I don't have the solutions, let me know. But I'm just seeing regression. Yeah, I could put the document here. So I'll add this document if it interests you, but you can create this yourself. This is just a layout. You don't have to have it so fancy with all the titles and everything. It's just basically the function. So what you're going to find, oh, I don't even have the risk and return documents here. Okay, I'm going to put them up. All right, so I'll put those up. So then there's some exercises I have here, reviews. So like I said, I have the answers for almost everything. What I don't have answers for, let me know. I can help you with that. What I want to look at right now is, before we go, in 15 minutes, I want to try a few exercises in the homework. Have you looked at this yet? These are pretty straightforward, but anyway, let's try a few of these. Let's look at number 3. So this is the homework for regression. What would be the right answer for number 3? I'll also put another assignment up on the platform for regression.
Would be B, as X increases, Y decreases.
So from a given set of data, Jack found that the value of a correlation coefficient of X and Y was negative 0.9. This indicates, so this is a strong relationship in the negative direction. So as X increases, Y decreases. That's a good interpretation. Let's go through the other ones. There is no linear relationship between X and Y. No, you need 0 for that, but you also need a graph for that. Let's look at C. There is a cause and effect relationship between X and Y. No, you can't say that. Even though it's close to 1, you can't talk about cause. You need theory and you need an experiment for that. Jack has definitely made a mistake in the calculation. No, you got a number that's between -1 and 1, so that's okay. X decreases, Y decreases, no. So the answer is B. Okay, let's I want to get into the ones that are these ones here. There's a question. Okay, let's try 16. How would you look at that? What is your approach? What are you trying to do right now? Are you putting them in your calculator? What is your approach? To just look at these numbers.
I think a graph would be easiest because we show you.
Yeah, there's a few values. Make a little graph. Yeah, you can do a graph. That's probably the easiest, right? Than to set up your calculator and put everything in and scroll through. So we want to see that it's equal to 1. What does 1 mean? 1 means that they are on the line.
Perfect correlation.
That they're all on a line. So if I take A, so -1, 0, and 1. Oh, Maybe I gotta do it. So. X is -1. Y is 3, so I'm gonna put a dot here. Let me mark my axis. Sorry for the curvy crap. So X -1, Y is 3. X0, Y is 4. Dot. X1, Y 5. So that looks like a line, right?
Yes.
So this looks good. Look at the other patterns. As X is getting higher, Y is going lower and lower. So as X is getting higher, Y is going lower and lower. That's a negative relationship, right? So that's not the answer. This R is equal to +1. Here, as X goes up, Y goes down and then up. So that's not the pattern. Here, as X goes up, so if it goes 1, you can rewrite this to go X going up. So you could do 0, 1, 2 and reorder things. So it's 4, 3, 5. So it goes up and down. See, if you have to see it go in order. Here, steadily, X is getting bigger, Y is getting bigger. We just drew it just to see a nice line. Let's do these. These are in order. And it goes, it's up and down and up. So that's how you just look at these very easily to see. The only one we really had to draw was this, just to see that they actually fit nicely on a line. So you're following me? Okay, let's do one word one, or maybe we have time for 2 word ones. And then a prediction. Let's do a prediction. Let's do this one. This one I like. Try 15. Okay, how's it going? So which one is X and which one is Y? What's X and what's Y?
X is the year.
Right, so X and Y is the height. And this is the line that was estimated with the data. You could estimate it too, putting that in your calculator. So if the Olympics had been held in 1982, so there was no Olympics in 1982. Use the line to predict the height that would win. So we have to put in here 1982. And make the equation for Y hat. Do you get? Which do you get? A through E. So 1982 times 0.3856 equals plus 671.924 negative is 92.3. So it is B. Any questions? What's the other one I want to do? Let's try this 18. The last one, and then we'll say good afternoon. Buen fin de semana. Have a good week, and next week we start probability, but you should be working on probability, I guess, Thursday night, Friday, before the class. This test should not take you very long. Just don't waste your whole week on the test. You need to get started on probability. So what is your height? How many coins do you have with you today? In one of the classes, the correlation between height and coins was -0.3, What does this tell us? Short people tend to spend more money. Something is wrong because a correlation of negative 0.3 does not make sense. So this one is wrong. Shorter people tend to spend more money. Well, we don't know if they spent the money. They just have coins. It's actually the opposite because it's saying that the taller people have less coins, right? Because it's opposite height, coins. This is a backwards interpretation anyway. Carrying coins inhibits growth. We cannot say anything causal. Something is wrong because correlation cannot be calculated between height and coins. That's wrong. There's a tendency for taller people to have fewer coins. That's all we can say. All right. All right, guys. So I'm going to stop there and let me know if you have any questions. Work on preparing for probability next class. And that's what I have to say. I'm done with regression. You can finish your review of the exercises that I skirted over. Okay, I hope this helped. Good luck with your test.
Professor, I have a question about the exam. I did a chart, but it was a very simple chart. So I don't know if I should just include a picture or you want me to also include the Excel.
Yes, send me the Excel with the chart that you built. Yeah, I need the
Okay.
Excel. Yeah,
Thank you.
yeah. And remember, I want your solutions handwritten anyway, so don't send me a Word document with everything written by hand. That's not, I mean, typed in. I want it handwritten.
Okay, but to that question, if we do it in Excel, then we can send you the Excel version and we don't need to send you the handwritten separately, right?
You think you're gonna answer everything in Excel?
No, not everything, but the ones that we do answer in Excel, we don't need to have a separate handwritten, right?
The only risk of sending just Excel is that if you did it all wrong, I don't know what you did. So if you did normal distribution in Excel, you know, it would be nice to have you draw the normal distribution, show me what you're getting, calculating. That's what the handwritten is for the
Okay.
normal. Okay, have a great day.
You too. Thank you very much.
Thank you.
Thank you, you too.
Good luck,
Bye.
everyone.
Yes.